Dear all, let's start lectures on mathematical analysis 1, and today's topic is critical points and extrema of the function. So first of all, let's give the definition of the critical point. What is it? First of all, so we say that x equals to c. You can see it is the here, and it is a critical point of the function f of x if f, c exists and either of the following are true. So here it should be, first of all, f prime c equals to 0, or the second condition here is f prime c does not exist. So here, to be critical point, we have derivative of first order derivative, of course, so it should be equal to 0 or it doesn't exist. So, or we can say this kind of points, critical points, also stationary points. Stationary points. Stationary points. So, now, let's give the first example to find critical points. So here we have now function f of x. So it's given function, and we need to find here critical points. And what should we do? Of course, firstly, we need to find here f prime. So f prime of x here, what is it? F prime of x in this case. Here also you can see the solution. So f prime of x here is equals to 30x fourth plus 132x cubed and minus 90x squared. So in this case, we need to just factorize by x, and then we get here next expression. So here we have, after factorizing, here we get 6x squared, 5x multiplied by 5x squared plus 22x minus 15. So now, to be find critical points, by the previous definition, we need to find what? Correct, we need to find here prime in equating to z, equating to 0. So here, after equating 0, what we get here? This is the last condition here, so you can see it is equals to 6x squared times 5x minus 3 and x plus 5. So, and each one we need to equating by 0. So 6x squared equals to 0, and this is the first one. Then 5x minus 3 equals to 0. This is the second root here. And x plus 5 equals to 0. So here we have now 3 corresponding roots of these equations. So the first one is equals to x equals to minus 5. Yes, from the third one. And from the second one here, x equals to 3 over 5. And the last one here, x equals to 0. So here we have 3 solutions, and these solutions called critical points of the function. So as you can see, here we have 3 critical points. You can see it is minus 5, 3 over 5, and 0. Now let's consider the example number 2. So determine all the critical points for the function. So, and now our function is g of t, which is given by this formula. So here, again, what should we do? Find derivative, first order derivative of the function. So after finding first order derivative, here we get this kind of expression. So here, what is it? It is 10 over 3, you can see here t power of 2 over 3 and minus 2 over 3 t power 1 over 3. So it's very easy to find derivatives here, of course. And now our expression, after simplifying, we have this kind of expression after simplifying. Now again, to find critical points using our first definition, so equating by 0 and find all zeros of this equation. So in this case, what kind of zeros here we have? Of course, there was a condition, so it should be equal to 0, first one, and this is satisfied. So f prime does not exist. So in our case now, here, after equating, so as you can see here, we have 10t minus 2 equating by 0. Then t here equals to 1 over 5. So this is the first critical point. Then find next one. Here we have, at the denominator, we have 3t to the power of 1 over 2. So if we're equating by 0, what we have? We have here t equals to 0. Yeah, so t equals to 0. Now it gives us, but of course, denominator cannot be equal to 0. So it means that here we have again two critical points, 1 over 5 and 0. So here, this is way to finding all critical points of the function. And why we need these critical points? Question. So we need this kind of critical points to define maxima and minima, so extremum points. Let's consider the next example here. So this is the same almost. So here we have now another function, polynomial. So here you can see 2w cubed minus 7w squared minus 3w minus 2. So, and find all critical points of the g function. After finding derivatives here, and what will be derivatives in this case? So g prime of w, it is equals to, here also it's written in the solution, so it is just 6w squared and minus 14w, yes, and minus 3. So, and derivative of the constant, it is 0. Okay, now equating by 0, this one. After equating by 0, here we have now quadratic equation. And this quadratic equation we will solve using determinant, or we can just divide by 6 and find solutions by Weir's theorem. This is very easy now. And here we have, after finding solution of the quadratic equations, so here we have two roots. As you can see here, we have two roots. So it is so here we have two roots, and these two roots will be critical points of the function. Okay, so here the next example, and now I think it is clear for you how to find critical points of the function, so using derivatives. So as I said, it's also called stationary points. So I will leave here this example for you as homework. Now we have with trigonometric functions, Vt equals to sine. So, and here sine squared 3t plus 1. So again, find derivatives here. And what will be derivative of the, let's consider separately here, sine squared 3t. And derivative of this one is equals to, and what it gives us, as you can see here, we have 2 times sine 3t multiplied by cosine 3t, yes, and multiplied by 3, this constant. So it gives us here this kind of function. So, and a prime here equals this one. Of course, we can just equating by 0, these two of them. So here separately, this is equals to 0, and also this one equals to 0. And here we have two equations, sine 3t and cosine 3t equals to 0. Now, equating by 0, we get here the following solutions. Here we have all zeros of these equations. This is now a trigonometric equation, and I think it's not so hard to solve here. Just equating by 0. Here we have two equations separately. So this one, sine 3t equals to 0, and the cosine 3t equals to 0. So when sine t equals to 0, when it is 0, and when it is 0 and pi plus 2 pi n, so here pi over 2 and 3 pi over 2 plus 2 pi n. Okay, and here you can see all critical points. They are all critical points here. So, and of course it will be with period. Okay, now next function here, exponential function now, and now again find here derivative. So after finding derivative, what we get here, this kind of equation, yeah. So, and this equation gives us exponential function cannot be here 0. That's why here we have only one equation, 1 minus 2x is 0. Hence x equals to 1 over 2, which is the solution of our equation, and it gives us critical point. So x equals to 1 over 2 will be critical point of the function. Now, as I said, why we need these critical points? Of course, we will consider in next lectures how to find using derivatives, maxima and minima, and relative maximum and relative minimum, of course. So, but here now we will study it by the definition, by the following definition, finding maximum and minimum of the function. So let's consider the first definition again. Here we say that f of x has absolute or global maximum at the point x equals to c. So here, if f of x less than or equals to f of c for every x in the domain which we are working. So it gives us now absolute maximum here. When? So here it should satisfy this condition. At x equals to c, f of x should be less than or equals to f of c. So, and now let's give the relative or local maximum. So the first one is global maximum, or we can say absolute maximum. The second one here is local, or we'll say relative maximum. So the relative maximum is here. Now you can see the difference between them. So in the first definition here, it should be in the domain, yeah, which we are working. Now, if it is local, so it will be for some open neighborhood of the point x equals to c. So here we need to consider now. So the neighborhood, and you know what is the neighborhood of this one? So the neighborhood, let me recall one more time. If it is point c, which we considered, so here we have c plus epsilon, and here we have, when we continue on the left side, here we have c minus epsilon. So this is neighborhood of c, and we will consider here a function in this neighborhood. So that difference, let me repeat one more time. Local will be here, so in this neighborhood, global in whole domain. Okay, so and similarly now we will consider here absolute or global minimum and relative or local minimum. So here there are difference between maximum and minimum. So here we can see f of x should be greater than f of c, and then we can say it is minimum. So greater than or equal. In maximum it should be less than or equal f of c, and then we call x equals to c, we have maximum respectively, or x equals to c, we have minimum. Okay, so and these points, maximum and minimum points, will collectively say extrema of the function. Extrema of the function. Okay, here one example. So as you can see here, we have the given function, graph of the function, and we need to find here absolute minima, relative minima, or relative maximum and absolute maximum, for example. So here you can see this one, this point is absolute minimum. Why? Because it's least one. You can see in this graph, in this domain, in this given domain. So, and here we have relative maximum, relative or local maximum. Here we have relative minimum, yeah? And here we have absolute, and also we can say relative maximum. So here we have this kind of 4 extrema points. Okay, now again consider the function f of x and identify all of the relative extrema and absolute extrema of the function. So here we have this point, for example, 4, 5. What is 4, 5? It is this one. So this point will be absolute maximum. Here it is the greatest value here. It reached to the greatest value at this point. So it will be absolute maximum. And absolute minimum will be here. When 2 and -6. And also we have relative maximum here, yes? And what kind of point is it? -1, 2. And also 4 or 5 we call also relative maximum with respect to this given neighborhood. And here relative minimums, here we have this one, yeah, and this one again. Now, so next example, identify the absolute extrema and relative extrema for the following functions. So f of x is equals to x squared on -1, 2. And now let's consider the here solution. So here our domain is this one, interval, closed interval -1 and 2. So, and now what is here minimum or maximum do we have? So of course here we have. So here you can see point 0 will be absolute minimum. Absolute minimum. And here absolute maximum is here. This is absolute maximum. Now, but here it doesn't have any relative maximums. Why? Because at the point -1, it's not relative maximum here, since it is the end point of the interval. That's why we cannot consider here neighborhood of the -1, because the left side of -1 we don't have, and correspondingly left side of 2 we don't have, because here right side of 2. So here, because 2 and -1 are endpoints of the intervals. Now, again, find absolute extrema and relative extrema for the following function. F of x equals to x cubed on -2 and 2. So, and here, do we have maximum? Of course we have here. This is absolute maximum, and this one is here absolute minimum. Yeah. So, but they are not relative maximum or relative minimum. Why? Because again, they are end points of the interval. That's why they cannot be relative. Next, so identify the absolute extrema and relative extrema for the following function. F of x equals to cosine x here, and let's take any here restrict, for example, domain. So for example, it will be now here we have, for example, -4 pi, and here we have 4 pi. So, and here you can see relative and absolute maximums of 1 at this point, and here relative and absolute minimums of -1 at the following points. Okay. Now let's consider Fermat's theorem. It's very necessary for us for the future work. So if f of x has a relative extrema at x equals to c, and here f prime exists, so it has a derivative first order, then x equals to c is a critical point of f of x. So it will be, in fact, a critical point such that f prime c equals to 0. For example, let's consider any example. Here also it's written f of x equals to x squared. And what will be here? Derivatives of this function, it is of course f prime x is here 2x. And after equating by 0, here we have x equals to 0. It is critical point. So again, if it has relative extrema at the point x equals to 0, then x equals to c is a critical point of f of x. Okay, now, but here you can see it's not gives us the inverse result here. For example, f of x here, x cubed in this case, and a prime here is x squared, and after equating by 0, x0 is critical point, but it's not extrema point. So in reverse order, it's not working, this theorem. It works only one side. Okay, finding absolute extrema. So finding absolute extrema, it is finding maxima and minima on the given interval AB. So to be find it, firstly we need to do the list of this following work. So the first one is verify the function is continuous on AB, then find all critical points here f of x, and then evaluate the function at the critical points which we find in the previous step, and then find all values at the endpoints. So endpoints here A and B. So here again we need to find all critical points, then find corresponding value in these points, and of course find the corresponding value and at endpoints. Okay, so and then identify the absolute extrema. For example, here given the function f of x 8x cubed plus 81x squared minus 42x minus 8 in the given interval, so minus 8 and 2. What should we do again? So we will find all critical points here. Firstly, it's necessary. So after finding all critical points, so here we have two critical points, minus 7 and 1 over 4. So, and then find here corresponding values at these points, minus 7 and 1 over 4. So here you can see, and when it's minus 7, it's equals to this number. When it's 1 over 4, it's equals to this number. And also we need to consider here corresponding values at endpoints. Here it is minus 8 and 2. So let's find here when it's minus 8 and 2. So when it's minus 8, it is this one. And when it's 2, we obtain the next result. So as you can see, here we have 4 values, corresponding 4 values. And let's compare them. And the biggest one will be absolute maximum, which is equals to this one. It is biggest one, yes. And the least one here is, of course, at the point 1 over 4, it is equals to minus 13.3125. So here you can see two corresponding values, extrema, absolute extrema, so maximum and minimum. Now, so here next example we have, so the almost same one again. It's given polynomial function, and here we need to define all critical points, and the critical points here are minus 2 and 1, and again put it to the given function, not to the derivatives, to the given function. So, and here we have the corresponding values, 24 when it's minus 2, and when it's 1, it is minus 3. And then again at the endpoints here, endpoints are minus 4 and 2. So here when it is minus 4, it is minus 28, and when it's 2, it is 8. So again, let's compare all of them. And here we have absolute minimum. What is absolute minimum now? Minus 28, which occurs at the point t equals to minus 4 at the endpoint, and the greatest value here is 24, which occurs at the point minus 2, which is critical point. So you can see here it can be value for critical point and also endpoint. So the next one here, next example, determine all absolute extrema of this function. And here also we have the same situation, and first of all find all critical points again, and then find compare them and all values at the end point here minus 10 and 0, and define absolute extrema. Okay, it will be unique also, of course, absolute maximum and absolute minimum. Now, any other examples you will consider at home? Thank you for attention. We'll continue the lectures.